Hello and welcome to Boxer's Shorts. I'm Adam Boxer and I'm a science teacher trying to help you understand more of GCSE science. In these short videos I will try and take difficult concepts from GCSE science, break them down, help you understand them, and then do some practice questions on those concepts. In terms of some general tips for using these videos, definitely do not have your phone on or anywhere around you. It's a distraction and it means you won't be able to concentrate properly. The same applies for other tabs on your computer, so don't have your social media tabs open on your computer or laptop, it will just distract you. I'm going to ask you to do some questions. If you don't actually do them, you won't actually learn anything, so make sure when I do ask you to do those questions, you do them. And finally, let me know in the comments if there is a topic that you want me to cover. Thanks for listening, and remember you can subscribe and just let me know if there's something you want me to do for you. Alright, last time I left you with a dramatic cliffhanger. We were looking at efficiency, we were looking at dissipation, and I left you with a problem with two cars. We're going to look at how to solve that problem today by use of the efficiency equation, or equations. But before we do that, just another reminder, turn your phone off, turn your notifications off, move your phone into a different room. Same applies for all the tabs that you might have on your computer or your laptop. Let's get started. Last time, I had two cars. I had car A and I had car B. Car A stored 1,500 joules. Car B, no, sorry, the other way around. Car A was storing 1,000 joules and car B was storing 1,500 joules. They both waste energy. How much? Car A wasted 200 joules, car B wasted 400 joules, if I remember correctly. Now the question was, out of these two, which one is more efficient? And in truth, you could probably work that out. It's a bit more complicated than if I'd given you the same amount of energy that they were storing. So, you know, if one was 1,000 joules, the other was 1,000 joules, and one wasted 200, the other wasted 400, it's obvious which one is more and less efficient. In this one, it's a bit more complicated because these numbers to start with are different and these numbers are different as well. In reality, it's not that hard because if I look at the difference between 1,000 and 1,500, well, I need to add another 500 here, which is roughly half of the 1,000. Well, it's exactly half of the 1,000, which means to get from 1,000 to 1,500, I'm timesing this one by 1.5. And I'm imagining, well, look, if car A had been storing 1,500 joules, how much would it have been wasting? Well, it's going to be wasting more than 200. It's going to be wasting 1.5 times as much, which is 300 joules. So I look at that and I think, well, if car A had been storing 1,500, it would be wasting 300. And car B stores 1,500, it wastes 400, which means that this one is more efficient. Essentially what I've just done there is a ratio. It's a way of looking at one number compared to another. And this leads us on nicely to the energy efficiency equations, because even these numbers are fairly straightforward. You know, you can look at 1,000 and say, right, well, to get to 1,500, I just need to times it by 1.5. That's pretty easy. But good luck doing that when you've got crazy numbers with decimal places. It's just too complicated. So instead, we do a very, very simple equation, which is just a way of looking at the ratio between these two things. And I describe, therefore, my efficiency as, and this is a bit wordy, it's the useful output energy transfer divided by the total input energy transfer. So if we go back to our previous example, so we had the car, so it was car A, I can't remember, stored 1,000 and it wasted 200 joules. Now I can just substitute those two numbers straight into there, because the useful output energy transfer Actually, no, sorry, there's a bit of complication first. I can do the bottom bit really easily. Total input energy transfer is 1,000. I don't need it to be that long. That's like laughably long. 1,000 joules underneath. At the top, I want the useful output energy transfer. That tells me how much is wasted. So that's what's wasted or useless. That's the stuff that I don't want, which means I must have 800 useful, because the remainder there has to be 800 joules. That's ironic. My phone was on. I'm going to turn it off right now. Off. Goodbye. Sorry about that, guys. So 800 divided by 1,000, which gives me 0.8. And again, you plug it into your calculator. Now what that number means is for every joule of energy in, 0.8 of those are useful. So every 1 joule in, 0.8 are useful. So in this example, I have 1,000 joules going in. I'm only getting 0.8 from each of them. That comes in total to 800 joules. So 1,000 joules go in, 800 joules come out, which means for every single joule that goes in, 0.8 are useful. Now at the beginning, I said to you that there is potential to say that this is two equations, and indeed in your syllabus it is written as two equations, because you could also write it as, or you'll also sometimes see it as useful power output divided by total power input. Now what this means is that if you have a question where it gives you your values not in joules but in watts, you just use those in here. So it's no different, it's just about using watts instead of joules. Right, let's do a simple example to illustrate that. So where you're given your values in power instead. So let's say you've got a device has energy transferred to it. So energy is transferred to the device at 75 watts. And it transfers, i.e. the device transfers 32 watts usefully. Okay, so how do we do this? So again, I use the same method that I always use, which is the DESCU method. The D is the data, so I'm not going to write the whole total input power, so useful power input and useful and total power input over here. So what I'm just going to write is power input, and that would be 75 watts, and useful output equals 32 watts. My equation is going to be efficiency equals output divided by input. I substitute, I have output, I have input, which gives me 32 over 75. I calculate that, so I get my trusty calculator. You do not do it in your head, as I've told you before. And that gives me 0.426 kind of recurring, and I'm just going to round that to 0.43. I'm just going to round that, and there are no units because it's a ratio. Because what that means is that for every watt that goes in, 0.43 watts go out usefully. Let's do one more example before you do some practice questions yourselves. So let's say you had a device has a 0.83 efficiency and transfers 260 joules usefully. What's the energy input in this case? What is the energy input? Now this one is ever so slightly more complicated. My data, okay, I've got efficiency equals 0.83, and I've got my output, or my useful output, is 260 joules. How much energy went in? So I write out the equation, and I'm just going to summarize. E for efficiency equals output over input, and I substitute, which gives me 0.83 equals output, which is 260, divided by my input, which is what I'm trying to figure out. I don't know what that is. Now again, I've told you many times, if this were maths, you'd be able to solve this no problem. Okay, if this were, I don't know, 4 equals 2 divided by x, everybody would know how to solve that. You just multiply both sides by x, and you'd get 4x equals 2, and then you go x equals 2 over 4, x equals a half, or 0.5. Easy peasy. So we'll do exactly the same thing over here. I'll do 0.83 times the input, so times both sides by input, and that equals 260. Input equals, I'll divide both sides by 0.83, which equals, and I get my calculator out, 260 divided by 0.83, and that gives me 313.25, and my unit there is joules, because that's what I've just worked out. I've worked out the energy that was put into this device. Alright, you're now ready to do some questions for yourselves. As per usual, do the questions, pause the video, do the questions, and then when you're ready, press play. Okay, so answers. Question number 1, the total input energy transfer, in this case, has to be 470 joules, because that's what it's used. It's used 470 joules. The total output is also going to be 470 joules, or 180 plus 290. It's because of the conservation of energy. The energy out can't be any more or less than the energy in. How much of that is useful? 290 is useful, because heating is not useful. You don't want your bulb to get hot. That's not a good use of the energy. You want it to be radiating that energy as light. And therefore you need to calculate the efficiency, which would be 290 divided by 470, which should give you 0.617 or 0.62. The remaining answers are now going to be up on the screen for you. Oh, hang on, sorry. There we go. Okay, so if you got all of those correct, well done. If you didn't, then have a look, have a check, go back. You might want to start again from scratch. If you are happy with that, you can move on to the next set of questions, which are appearing on your screen now. And as per usual, pause the video, do the questions, and then unpause for the answers. The answers to that are now here. If you got all those right, well done. If you didn't, go back, check your working. It might be a good idea to go from scratch. That's the end of our video on the efficiency equations. As per usual, thank you for watching. Please do subscribe if you want to see more videos like this, and let me know if there's any particular topics you want me to do. And on next videos, we'll cover more energy equations, and then moving on to energy sources.